Welcome to today's Explainer. It's kind of wild to think about. We have thousands of programming languages out there, yet we really only rely on a select handful to build our entire digital world. Today, we're going to enthusiastically demystify exactly how these languages, the ones forming the backbone of our digital infrastructure, are actually designed right from the ground up. If you've ever found yourself wondering why one codebase looks completely alien compared to another, or why some languages are insanely fast while others just read like plain English, well, you are definitely in the right place. We're going to unpack the precise architectural foundations that make all these systems tick.
Here is our blueprint for today. We'll be looking at 1. Purpose and design goals, 2. Syntax, semantics, and meaning, 3. Memory and type systems, 4. Flow and abstraction, 5. Execution and ecosystems, and finally, 6. The art of trade-offs.
Section 1. Purpose and design goals, the foundation of every language.
So languages don't just happen by accident, right? They're born with a very specific mission, and that mission literally dictates the day-to-day life of the developer using it. If pure, raw performance is the goal, designers build something like C, basically handing you the keys to the hardware. But if human productivity is the top priority, you get Python, which focuses heavily on just making code easy to write. Then you have Rust, which prioritizes absolute memory safety to prevent crashes, and Java, championing that classic write once, run anywhere portability. This intended purpose absolutely sets the stage for every single architectural decision we're about to explore.
Section 2. Syntax, semantics, and meaning, the surface layer.
Okay, so there's this constant tug-of-war going on between the visual rules of syntax and the functional reality of semantics. Syntax is essentially the vocabulary on your screen. It defines the rules for keywords, operators, and formatting. And let's be honest, developers will happily argue for hours over syntax formatting, tabs versus spaces, where the bracket should go. But semantics are what actually dictate whether the code works. Semantics go completely beyond that visual structure to define exactly what the code does when the machine gets its hands on it.
Because think about it. Beautiful syntax is entirely useless if the computer misinterprets what you want it to do. Semantics are what dictate that invisible, behind-the-scenes behavior. When you type a command to add two variables or you set up a loop, the language's semantics execute that specific action. And honestly, a misunderstanding of semantics is exactly where the most frustrating, silent, late-night bugs like to hide out.
Designers actually tackle this whole concept of meaning from 3 distinct angles. First, operational semantics, which describes the literal step-by-step gears turning inside the machine. Then there's denotational semantics, mapping the code directly to rigorous math. And axiomatic? That's for when you absolutely positively must prove that the program is fundamentally correct. It's a really cool multi-layered approach to giving just plain text some serious power.
Section 3. Memory and type systems, the hidden machinery.
Now we hit the language architect's ultimate dilemma. How on earth do we catch errors before they cause an absolute disaster in production? This creates a massive architectural conflict. Do you enforce strict safety up front with static typing? That's basically building a fortress against errors before the program even runs. Or do you prioritize high-speed, flexible development with dynamic typing? That means accepting the risk that a fatal error might only show its face when the code is actually running live. It's a huge trade-off.
And memory management, that is a constant, brutal battle between raw performance and developer sanity. Manual management, like what you see in C, gives you total control. But man, one wrong move and you've got a massive memory leak on your hands. Automatic garbage collection, found in Java or Python, gives developers a break by cleaning up memory automatically, but it risks these random performance hiccups. And then you have Rust's ownership model, which is this brilliant, strict compromise enforced by the compiler itself to balance safety and performance.
Section 4. Flow and abstraction, managing complexity.
To direct the flow of execution, languages have had to evolve way beyond basic if statements and while loops. To handle what we demand of them today, they've adopted some incredibly powerful mechanisms, things like pattern matching, coroutines, and async await. This is what allows programs to juggle complex, concurrent tasks smoothly without bottlenecking the entire system. But here's the thing, raw logic scales terribly. To keep human developers sane, languages have to offer abstraction paradigms. Maybe that means wrapping data up in Java's objects, chaining pure mathematical functions in Haskell, or just grabbing a multi-paradigm approach like Python does. These are the crucial mental models that let us build massive, sprawling systems without completely losing our minds in the sheer complexity of it all.
Section 5.
execution and ecosystems, the living language.
When it's time to bridge the gap to the physical hardware, designers face another massive strategic choice. Do you use a compiler, this heavy-duty translator that perfects the highly optimized machine instructions before anything even runs? Or do you rely on an interpreter to agilely process the code sequentially, line by line, right on the fly?
Just look at this modern execution pipeline. First, we write the syntax, and then that middle layer goes to work. What's absolutely fascinating here is that a lot of modern languages flat out refuse to pick just one path. Instead, they use a hybrid approach. They compile it down to an intermediate bytecode and then run that through a virtual machine. That right there is the secret sauce for achieving incredible cross-platform portability before the hardware actually executes a single instruction.
But let's not forget, a language is absolutely nothing without its ecosystem. It needs a survival kit, rich standard libraries so we aren't reinventing the wheel every time we need to handle data or networking, crystal clear error handling, and robust concurrency models. But you know what the ultimate tightrope walk is? Evolution. A language has to grow and add new features without breaking the millions of lines of legacy code that are already holding the world together. Backward compatibility is a terrifying, amazing challenge.
Section 6. The Art of Trade-offs. Finding the Balance.
So here's the bottom line. There is simply no perfect language out there. None. There is only a series of carefully calculated sacrifices to achieve a specific goal. If you optimize for pure machine efficiency, you're probably going to sacrifice human usability. If you lock down safety, you might slow down your development speed. A truly well-designed language is just one that aligns its particular set of trade-offs perfectly with its intended purpose, remaining consistent and expressive throughout its entire lifespan.
So the next time you sit down, fire up your IDE, and start writing code, take just a second to recognize the brilliant, invisible architecture powering every single keystroke. Think about it. What trade-offs do you value most? Are you chasing ultimate speed, ironclad safety, or just the pure joy of a really clean syntax? Thanks for joining me for this